College Algebra, the review chapter, section 8, nth roots and rational exponents. What is objective 1? Work with roots. Oh my gosh, what in the heck does that mean? Well, first of all, what do we mean by roots? Well, the nth root of A, if that equals B, this is the index, this is the radical sign, the vinculum, and this is the radicand, but that is the same as A being B to the nth power. So one way we can solve this is take both sides to the nth power if we want to solve for A. Now sometimes we've got problems here because n could be even or odd. Now, if n is odd, then we got no problems. A and B are elements of the reals. It can be any real number. So n being a 3, 5, 7, 9 is really sort of easy. But if n is even, we've got problems with square roots and quartic roots, fourth roots of negative numbers, which gives us complex numbers. So what we're going to do, we're going to have to say that A and B are both greater than or equal to 0. So that just makes everything sort of nice and keeps everything out of that complex zone, so to speak. Objective 2. I'm going to do a bunch of examples at the end of all these objectives, I guess. Simplifying radicals. Well, a simplified radical, there are a couple things you need to look for, I guess. If we go back to the nth root of A to the m, we'll call it. For a radical to be simplified, m must be less than n. The exponent for the radicand must be less than the index. Also, m and n can have no common factors. M can't be 2 and n 4, because we could then reduce that and make this a nicer, take out that common factor. So any of this stuff now, this is once you got this written as a prime factorization underneath here. So if you've got 9 squared, it's really not 9 squared. You got the 3 that you can also use, 3 squared squared. So it's 3 to the 4th. You've got to make sure you got all that set up in its most simplified form. So we got some things, though, we can do with radicals. If you've got the nth root of A times B, you can split that up into the nth root of A times the nth root of B. If you've got the nth root of A over B, same thing. So for multiplication and division, we can split things up. The nth root of A over the nth root of B. And if you have the nth root of A to the mth power, that can be inside the radical, that can be outside the radical, whichever works best for you, so to speak. So there are ways of reducing it with that thing. What are like radicals? They have the same index, the same variable in the radicand, to the same power. So in one sense, that nth root of whatever this radicand is That part has to be exactly the same. The numbers out front, if there was a 5 out here, that would be 5 of these radical expressions. So this whole chunk of notation is what will make this like radicals. To combine like radicals, it's just like using variables. The square root of 2 plus the square root of 3 cannot be combined. 2 times the square root of 2 plus 3 times the square root of 2 can be combined because we're talking about like radicals. That's 5 square roots of 2. So you can do things like that, but they've got to be like radicals, and you're really just saying how many of these radicals you have when you add them together. So, what is objective 3? Rationalize denominators. And I always wondered about these when I was a student. If you have 1 over the square root of 2, that is not simplified. You must rationalize the denominator, which is multiplying by something that will make the denominator, at worst, a rational number, a fraction. In most cases, it'll make it an integer, but they don't call it integerizing denominators. They call it rationalizing. So if I multiply both numerator and denominator by the square root of 2, which is really just multiplying by 1, I get the square root of 2 over, well, this becomes the square root of 2 squared, or 2. And I always wondered, they said that was simpler, or simplified, when 1 over the square root of 2 was not. And I always wondered, why in the heck, why is this simpler? It's got more stuff. This has got a 1 in it. Isn't that simple? Well, it really goes back to before calculators. If we have 1, and we wanted to divide by the square root of 2, which we can't write exactly, we'd have to do 1.414 and then keep on going. You have to figure out what you want to divide by, and we'd have this division problem. Or, if you look at this form, you have the square root of 2, which you can take out as many places as you want, and you're dividing that by 2. So which would you rather do? Dividing by 2 is so much easier. You could do that really quick. Into 14, it goes 7. 2 times 7 is 14. Then it's another 0 here, and then another 4, so it's 0.707. So this is so much easier than that. That's why this form is simplified, and 1 over the square root of 2 is not. So in many cases, we'll multiply by itself if it's square roots. Suppose I have the cube root of 2. Well, what you need to multiply by is enough stuff to make this denominator, in this case, an integer again. So I need the cube root. You're going to use the same root index. But I can't just have 2, because that would just be 2 squared, and the cube root of 2 squared isn't anything special either. I need 2 squared here so that I can get the cube root of 2 cubed. That's when I get just the 2 in the denominator. And the numerator takes care of itself, really. So I'm not going to even write that down. This could be the 13th power. And what would I need? I'd need 12 more 2's to get this to the 13th power, to get this to just a 2. It doesn't matter what the index is. You need to have the radicand able to sort of cancel that exponent. Now, there's also another situation that brings up our a plus b times a minus b. What do you get when you multiply that together? Do you remember this special product? This is a squared minus b squared. And that can be used when you have something like this, the square root of 2 minus the square root of 3. How do I rationalize that denominator? Well, I've got to multiply by something that makes these square roots not square roots. So I can multiply by the square root of 2, and that'll get rid of this one, but then I also have the square root of 6. And if I multiply by the square root of 6, then I make this 2 times the square root of 6. And you just keep back and forth changing things. What do? This is like the a being the square root of 2 and the b being the square root of 3. You multiply by the square root of 2 plus the square root of 3. Both numerator and denominator. Now that leaves the numerator, which, just like I said, not going to concern this. Hopefully you can do this no problem. But now you got the difference of 2 squares here in the denominator. It's the square root of 2 squared minus the square root of 3 squared, which gives us that stuff over 2 minus 3, or a negative 1. Now, another situation might be, and this one would be hard to see perhaps, remember our sum and difference of 2 cubes. So if you have a cube root, try to remember this combination, because you might be able to use one of these on the right side to multiply both numerator and denominator to get rid of the cube. That's a little bit fancy, but that can happen. We'll may have to give you an example of that, but not right now. Okay. What about objective 4? Let's make sure I can get a new screen here. Okay. Simplify expressions with rational exponents. What does that mean? Well, what are rational exponents anyway? Well, they're exponents that are rational numbers. Fractional exponents maybe is a better name. So how do you translate that? The nth root of a to the m can be written as a to some power. M, the exponent for this radicand, will be the numerator. The index will always be the denominator. So you can essentially use these exponents or radicals as fractions. For example, suppose you have 9x squared y to the 1/3 power over, this is an x squared, x to the 1/3 y, and that's all to the 1/2 power. Well, you can write this, I guess, as cube roots and square roots, but that really doesn't help you figure this out. It's better to use the exponents, because this will follow the laws of exponents. And now we can expand the laws of exponents. Expand those to rational numbers. Fractions. You just got to be a little careful. The square root of a negative, or a negative to the 1/2 power, is going to be a complex number. You can't really do that. So, just like we could before, this 1/2 can be applied to everybody inside here. So it's 9 to the 1/2. It's x squared to the 1/2. It's y to the 1/3 to the 1/2. it's x to the 1/3 to the 1/2 and y to the 1/2. See if we can write this as a final answer here. 9 to the 1/2 is just really the square root of 9, or 3. X to the 1 to the squared to the 1/2, you multiply, and you get x to the 1st. Y to the 1/3 to the 1/2, when you multiply fractions, numerator times numerator, denominator times denominator, 1/6. Here the same thing, x to the 1/6 and y to the 1/2. And now we've got to combine these x's and y's, and I'm going to run out of room. So, yeah, I guess we need to go to the next page. Let me make sure I remember this. I've got to write it down. Okay, let's go to the next screen. So we have 3xy to the 1/6 over x to the 1/6 y to the 1/2. Okay. So this is the 3. It's x to the 1st minus 1/6. Y to the 1/6 minus 1/2, right? Well, this is the 3 again. 1/6, or I'm sorry, 1 minus 1/6 is 5/6, x to the 5/6. And 1/2 is really 3/6, so 1/6 minus 3/6 is a negative 2/6, which really is 3/5/6 y to the negative 1/3, reducing that. But they'll probably say, and I will probably say on a test, make sure all your exponents are positive. So instead of a negative exponent there, we're going to write this as 3 in the numerator. Oh, this should be an x here. X to the 5/6 over y to the 1/3. And that's what I'm going to want to see as a final answer. All your exponents positive. Does that make sense? Let's do some more examples and show you how all this exponent, fractional exponent stuff can work. This is number 42 on page 77. It is 8xy minus square root 25x squared y squared plus the cube root 8x cubed y cubed. And we're asked to simplify. I'll probably give you more instructions than that. Write it, combine like terms, write it as a single, if it can be, a single term with the positive exponents, or maybe just say use positive exponents. Here's 8xy, can't do anything with that. But this square root, you can apply that square root to all this stuff. The square root of 25 is 5. Square root of x squared is x. And the square root of y squared is y. Apply this cube root to everybody. What's the cube root of 8? Well, 2 times 2 times 2 is 8, so the cube root is 2. The cube root of x cubed is x, and y cubed is y. Aha! These tricky guys. 8 minus 5 plus 2 xy's. That's left over with 5 xy's. Not so bad. How about number 50? This is the square root of 3 minus 1 over 2 times the square root of 3 plus 3. And they want to rationalize the denominator. Okay, so in order to do that, I've got to multiply by enough stuff. Let's see, square root of 3 minus 1 times something. 2 square roots of 3 plus 3, that's the key, this denominator. So how do I get rid of that square root of 3? I can't just multiply by the square root of 3. I'm going to have to use that idea of the difference of two squares. So I'm going to change colors here so you can see it. When you see things like this, you use the difference of two squares idea and say, okay, this is going to be 2 square root of 3, not plus 3, but minus 3. Do that to the numerator. So the numerator, let's see, this is 2 times 3, or just 6. This is negative 3 square roots of 3. Here's a negative 2 square roots of 3. And a negative times a negative positive 3. This one should be easier because you set it up. This should be the difference of two squares. It should be 2 square roots of 3 squared minus 3 squared. Numerator, 6 and 3 is 9. Negative 3, negative 2, which is a negative 5 square roots of 3. The denominator, squaring this, it's 4 times 3, or 12, minus 9. So finally, 9 minus 5 square roots of 3 over 3. Can you reduce this? Well, that 5 gets in the way. If this were 6, then you could divide everybody by 3. But it's got to be everybody. You can think of this as 9 over 3 minus 5 square roots of 3 over 3. And this you can reduce, I guess, if you'd like. But this one you cannot. So I would accept either way here. Okay. How about number 66? 8 over 27 to the negative 2/3 power. Now this one's just to simplify, but we want to write this with no negative exponents. So it's 8 to the negative 2/3 and 27 to the negative 2/3. Well, negative exponents usually mean you're in the wrong place. So put this 27 to the 2/3 over the 8 to the 2/3. Now they're in the right place. Those negative exponents, just the negatives disappear. Because 27 is 3 cubed and 8 is 2 cubed, we can use that to the 2/3 power. And we get 3 to the 3 over 1 times 2/3 over 2 to the 3 over 1 times 2/3. Now these 3's cancel, and you get 3 squared over 2 squared, which is 9/4. Did it need all those steps? Well, I wanted to go through all those to show you. It's probably better to do the roots before you do the exponents, the squaring and such. If back up here at 27 to the 2/3, you should look and see, is that base a perfect cube? So I could have said, you know, the cube root of 7 is 3, and then just left a square. The cube root of 8 is 2, and left a square. Still would have gotten 4 steps. Just so you understand, it's easier to take the roots first, if possible, than doing the squaring and then taking the roots. Okay. And last but not least, of course, number 74. See, 4x to the negative 1, y to the 1/3, Boy, does that sound familiar. I guess I didn't do it yet. Let's keep going. Y to the 1/3 over xy to the 3/2. This numerator is also to the 3/2. Okay. I guess we could have done the whole thing to the 3/2. Anyway, this should be 74. Now we can distribute this, so it's 4 to the 3/2. It's x to the negative 3/2. It's y to the 1/3 to the 3/2 over x to the 3/2, y to the 3/2. So all those laws of exponents we used before can still be used. So 4, can I take the square root of 4 right away? Yes. This is 2 cubed. This x to the negative 3/2 should be in the denominator with the other x to the 3/2. And this y to the 3/2 I'll put down here too. But now this becomes, this 3 cancels, and this is just y to the 1/2 in the numerator. Okay, so 2 to the 3rd is 8. X to the 3/2, x to the 3/2, you add these together, together. 1.5 and 1.5 is 3. Now, 3/2 is greater than 1/2, so I'm going to leave the y down in the denominator, because I've got to make sure these are positive exponents. And 3/2 minus 1/2 is just 2/2 are 1. You don't really need that 1 there, but it's nice to put it there, I guess, to emphasize. So it'll take some practice, but these are fun problems. See you in the next chapter.